Okay, so this is the second class for the principles of communication. In our last class, we discussed some random problems from the date sensing and the remote sensing worksheets and some other year question problems that you asked me about. And we did start the principles of communication chapter, and I talked a little bit about how these graphs, combination of these two graphs, the unmodulated carrier and the information signal, which is our main signal that we want to send from location 1 to location 2, these two can be merged in two different ways. Either we can do amplitude modulation where we can have this, or we can have frequency modulation where we can have this. There is a certain mechanism, methodology to achieve this kind of variation. I discussed in a very simplified, generalized version of how this is done. We're going to see some other parts for this for this thing. One important information I would like to tell all of you before I go down further is that every single image, every single figure that you'll be seeing showing up beyond this point, every one of those are applicable for AM, amplitude modulation. Your syllabus does not cover a lot of information about frequency modulation. There's only one figure that you have for frequency modulation, that is this one, to give you an idea of how frequency modulation changes the carrier signal. And that's it. Every single information that we're going to be seeing afterwards that is going to be coming beyond this point, after page number 28, they're all going to be related to amplitude modulation. It will be confusing somehow, and there are reasons for your confusion because there are certain things that I do not know how to explain because I didn't study these parts. Because to be honest, you would not required to explain those things, but there will be mention of some certain mechanisms which I wouldn't be able to explain, but I'll tell you what are the parts that I'm not explaining to you because that's not needed. So what I want you to remember, nothing beyond this point is relevant to FM. Everything beyond this point is relevant to AM, amplitude modulation. So I'd like all of you to read through these three paragraphs. Take a quick read through these three paragraphs. It's pretty much the same thing that we have discussed last class. If you have any question, you can ask me right now. I'll give you a minute. Thank you.
স্যার
বলো।
স্যার ওই যে লাস্ট ক্লাসগুলোর ভিডিওগুলো তো এখন আপলোড করেননি।
আচ্ছা, ওটা যে তোমাদের ক্লাস শুরু করার আগে করছি, ক্লাস শেষ হওয়ার পর পেয়ে যাবা, চ্যানেল অলরেডি আছে, মানে এইচডি ভার্সন কনভার্সন চলতেছে। দেখাই আমার চ্যানেল কই, এই যে লাস্টগুলো এখানে আপলোড করছি, যেখানে যেগুলো ডিলিটেড ভিডিও হিসেবে আসতে দেখা যাচ্ছে এগুলো এখনো আন্ডার প্রসেসিং আছে। So they are not basically deleted, they are still there under processing. Any question from these parts, anyone? এই পার্টটা কি বুঝা গেছে এখানে কি বলছে আমি এই জিনিসটা একটু বুঝাই কারণ এটা আমাদের পরে লাগবে The use of a carrier wave allows different radio stations in the same locality to transmit simultaneously. Each station transmits on a different carrier frequency and consequently the carrier waves do not, in effect, interfere with one another. This is because one receiver is tuned to the frequency of a particular carrier wave. The receiver then responds to and gives an output based on the difference in displacement or frequency between the actual waveform and the underlying carrier wave. In other words, the receiver recognizes the information signal and rejects others. এই জিনিসটা মানে হচ্ছে যে if you want to operate multiple different transmission station সেটা it can be TV transmission, it can be cellular transmission, it can be radio transmission, whatever. For most of the examples down the line, we're going to talk about radio transmission because that's we're going to talk about audio channel transmission. It's easier to deal with that. So you can think about for mobile communication or for radio communication, something like that. What they're trying to mean is that if we want to operate multiple transmission mechanisms or multiple transmission stations to in the same geographic area within overlapping geographic locations, then
স্যার আপনার ভয়েসটা একটু মানে লাউড দেখাচ্ছে
লাউড হয়ে যাচ্ছে
হ্যাঁ স্যার যে আগের মতো
আমি তো একই সেটআপে ক্লাস নিতেছি আগের মতো হচ্ছে না কেন আই হ্যাভ নো ক্লু হ্যালো শোনা যাচ্ছে না বলবান
জি স্যার শোনা যাচ্ছে
শোনা যায়
জি স্যার
if it is too loud I mean it is I'll tell you exactly what is happening here সেটা হচ্ছে the location the distance of my microphone from my lips to my microphone is not always same so it is usually horizontal to my mouth and sometimes I just bring it too close to my mouth so that's when the volumes can have a little bit of it. So currently I have placed it in the regular place that I usually go by. So I hope it will work out. Okay, what I was saying is time to say that if we want to operate multiple different radio stations within the same geographic region or overlapping geographic region, then we must make sure that these waves should not interfere with each other. Because if waves from multiple different sources interfere with each other by their inherent property, then at some locations they are going to produce constant interference, some locations they're going to produce destructive interference. As a result, locations where they will produce destructive interference, you will not receive any transmission. Those locations, if anyone tries to get a radio signal within a region where two different radio stations are making destructive interference, that will be sort of like a destructive interference region or like what can I say? The intensity of the wave at that location would be zero because the waves will cancelling each other out. As a result, that location would work like a radio darkness region. So in your transmission area, there will be certain locations, so there will be certain pockets or loops or certain regions where network is really bad. One of the things that actually happens in my classroom is that for those who uses GP phone, you might have seen over the duration of the last 4 years or 3 years that in my classroom GP network is really bad, like unbelievably bad. দেখছো না? There may be two reasons for this. One is that either my classroom happens to be on the very corner of multiple GP towers, they are really far away, or the type of barrier that I have, somehow we have that kind of problem, maybe. Now, if we can easily avoid that problem if we use different carrier wave for different radio frequency tower. So what I'm trying to mean is that what you're going to see soon, this information signal, if this is a voice signal for human being, the typical range for this signal can be from 20 kilohertz to 20,000 kilohertz. So 20,000 kilohertz, 20,000 hertz, 20 hertz to 20 kilohertz. That is a typical range for human audio range, human audio hearing range. So we can modulate this thing. Let's say with a frequency with a unmodulated carrier of let's say maybe with some value of unmodulated carrier which has a much higher frequency than the maximum frequency of this information signal, and they're going to undergo merging. Either we're going to do amplitude modulation or we're going to do frequency modulation depending upon what technology do we have available and what is cheaper for us to adopt. But the point is, if we have significantly different carrier frequency for different radio stations, if we assign them to different radio stations, then they can use different modulated carrier, different frequency of carrier wave within which they're going to be merging their own information signal. Or in other words, the practical scenario that I can tell you that if you're listening to radio in any part of the Dhaka metropolitan city, you can tune to different radio stations. You can have access to FM 98.0, 88.0, 88.8, 88.4. You have a lot of different options to go for the radio station choices. Well, how does that work? I mean, they're all transmitting their individual radio signal in all directions. So from your location, you could tune to any of those radio frequency radio station and you could receive that signal. So how is it possible that you are receiving signal of one specific radio station that clearly and you are able to reject other? The idea is that the antenna that you will be using to capture that wave information with certain electronics or with certain electrical mechanism, we can tune that antenna to resonate with a very specific carrier frequency wave of that station. Let's say radio frequency operates at 88.4. Am I correct? Whatever.
Yes, sir.
I think so. Radio frequency operates at 88.4 megahertz. So if we want to hear to that radio station, we can tune our receiving antenna at that exact frequency, which means now the 88.4 means radio frequency people or radio frequency owner, they have bought the microwave range of 88.4 megahertz for their transmission channel. They have bought the license to use that much part of the microwave channel from our government, from BTRC, Bangladesh Telephone and Telephone Communication Limited, BTRC. So they will modulate, their unmodulated carrier will be at that frequency, 8.4 megahertz. And within that, with that unmodulated carrier, they'll be adding whatever the information that you want to transfer, news, music, stuffs. So in true case, this information signal would not be as smooth as, for example, let's say they're playing some I Bet You song. So this is going to have a lot of different variation on the, what we call the quality of a sound. So you have a lot of different variations. They're going to add up all of these variations with this symbol, and we might as well come up with a realistic wave, the amplitude modulated wave that looks like this. This is a more realistic version, where you have not so smooth up and down. You have random ups and downs depending upon the quality of the sound. Maybe at this location we had on the symbol getting like it went at this point, so we had such a high spike. So maybe over here we had a drum roll going down. So you can have a lot of different variations for an actual sound, and amplitude modulation can look like this. This is a more realistic version for how an amplitude modulation should look like. This, on the other hand, a very unrealistic yet very simplified version to give us an idea that what is actually happening. Now, the point I'm going to make, whenever we assign different radio station, different transmission station, different carrier frequency, they will operate at that specific carrier frequency, and as a result, they will not interfere with each other's signal, because to have interference or to have superposition to happen, we need multiple waves to have the same frequency. In this case, we are precisely avoiding that phenomenon. আমার কথা কি বোঝা যাচ্ছে? ঠিক আছে, যেমন এটা আমি যদি আরো খুব সিম্পলিফাইড একটা এক্সাম্পল বলি, আমি জিনিসটাকে এত এমফাসাইজ দিয়ে এক্সপ্লেইন করার কারণ হচ্ছে এই জিনিসটা আমাদের একটু পরে গিয়ে আবার লাগবে। আরেকটা এমফাসাইজ করে জিনিস বলি, সেটা হচ্ছে মনে করো হচ্ছে একটা মাঠের মধ্যে মনে করো 10 জন মানুষ দাঁড়ায় আছে, ঠিক আছে, and they want to communicate with each other. It might prove very difficult to communicate with each other if they are standing in a circle and they are all trying with human voice. There will be noise, period. It will be very difficult to have communication. It might as well be possible that two persons on their two adjacent sides, they might be able to communicate. I mean, one person might able to be successfully communicating with two persons, which is on their right and on their left. But more than that, successful communication, more than that, might prove very challenging. But if you assign all of this person individual different carrier wave, and they're going to talk into a device, let's say mobile phone, and they're going to modulate their individual voice with that frequency, and whoever the two person want to talk with each other, they will tune their receiving antenna, sending antenna with their respective values, and they can work with that pretty well. One interesting thing, which is not discussed over here, but it's important that it is interesting for me to share. Let's say, whenever we use mobile communication, মোবাইল কমিউনিকেশন তোমাদের সিলেবাস থেকে অ্যাকচুয়ালি বাদ দিছে, আগে ছিল। সো এটা এখন পিএসটি নেটওয়ার্কের ফুল স্ট্রাকচার তোমাদের সিলেবাস থেকে বাদ দিছে, বিকজ at certain point of the CIP people thought that you kids should know this, and then later they thought that no, this is a bit too far-fetched for you, so for your brain capacity level. Either way, syllabus থাকলে তোমাদেরকে পড়াইতাম, যেহেতু নাই সেজন্য পড়াচ্ছি। বাট একটা জিনিস সিম্পলি বলি, the way our cellular communication works is actually to be honest really amazing, like unbelievably amazing. We take this technology for granted because we've been growing up and living up with this technology, seeing this available for us. But if you think about it, it takes a lot of thinking and achieving for it to come to this level. Whenever, let's say, if I'm trying to make a phone call through a certain tower, let's say my cell phone wants to make a communication with my network provider tower. I'm not so I'll say about two different things, because this will be actually available to important for us at a bit later part for this thing. এখানে কিছু ঝামেলা আছে, তারপর হচ্ছে যে এই জায়গাতে এসে আমাদেরকে আবার এগুলো নিয়ে কথাবার্তা বলা লাগবে যে কেন আমাদের কমিউনিকেশন গুলা এরকম হওয়া দরকার। So this is a part that I'd like to share right now in regard to this paragraph. সেটা হচ্ছে if I'm trying to make a phone call, let's say I have pressed a certain person's number, and I press the green button of my cell phone, and it is making a call. It means that at that point, before you even make a call or send an SMS to your network, your cell phone and the nearest tower of your network, they're always communicating. Network in this case, I mean your service provider, Grameenphone, Airtel, or Teletalk. That's what I mean by the word network. So this tower and your cell phone, they're always communicating. And as long as they're communicating, your cell phone is always assigned a very specific carrier wave signal for that duration, which can change every second or every half a second or every microsecond, I don't know. Or whenever you travel from one tower region to another tower region, it will change. Your cell phone has the capability to tune its antenna at any of this frequency value that the tower commands the phone to tune with. So the tower tells the telephone antenna that I want you to operate at this thing, at this value. Your cell phone antenna operates at that frequency. Whenever you make a call, this call happens through the communication channel, through the telephone network. The moment you start to talk through your phone, you add your voice to that specific carrier signal frequency which was assigned to your phone from the tower, and they do the merge. Typically, this merge happens by frequency modulation. Typically, normal modern telecommunication networks preferably use FM other than AM, because AM has some other problems. We're going to see about that. So it does the modulation, and then this signal is sent from your phone to the tower. Now here's the deal: your phone works as a transceiver. It transmits and receives at the same time. A walkie-talkie, on the other hand, does not. A walkie-talkie can also work as a transceiver, but it does not do the transmission receiving at the same time. For those of you who have ever used a walkie-talkie, you know how it works. For those of you who have never, let me just show you a sample picture of a walkie-talkie, and might as well be easier to understand. This is how a typical walkie-talkie looks like, and every single walkie-talkie, if you have a look at that, you can see there is a large button over here. These are the two things by which you can control your frequency channel, and you can choose your channel variation. This is the basic antenna, obviously, and this button that you can see over here, this is a press button. This button ensures that if you're pressing this button, your walkie-talkie will work at that duration as a transmitter. You will not be receiving anything. Whatever you say will be sending out to all the other walkie-talkies in the network. When the moment you you release the pressure, your walkie-talkie converts back into a receiver. So this device can also work as a transceiver, but not simultaneously, one at a time. It can either work as a transmitter or it can work as a receiver, but not both of them at the same time. Whereas cell phones, they work as both of them at the same time. You're talking to the mobile, the other person's trying, you can see here as well, you are receiving messages or other stuffs as well at the same time. So which means your cell phone needs to have both way communication simultaneously. How does it achieve it? That is achieved by a polarized wave. Both your cell phone and your cell phone tower, both of them operate at the exact same frequency, exact same carrier frequency, carrier wave frequency. But if your cell phone is sending a perfectly horizontal wave, the tower will be sending a perfectly vertical wave. So even if this is a straight line communication from your phone to the tower, within this path, these two waves will not overlap and make a mess up of maximas and minimas, because they would simply pass through each other because they are transverse waves. Now, at which angle this modulation should happen, the tower typically instructs that to the cell phone as well, that you are going to operate at this carrier wave and your modulating, your polarization angle should be this much. So all the information are fed from the tower to the cell phone, and the cell phone is designed to operate for a range of carrier frequency and for all the possible angle of polarization. This is how a both-way communication is achieved without interruption. Does it make sense so far? যে কথাগুলো বললাম এটা বুঝা গেছে কিনা? Maybe. No one can know because no one wants to respond. আচ্ছা, এখানে আমরা additional কিছু জিনিসগুলো দেখি। This is a pretty interesting part. Here it says, can you should be able to recall that the carrier wave amplitude modulated by a single audio frequency is equivalent to the carrier wave frequency together with two sideband frequencies. Important part. Amplitude modulated by a single audio frequency, amplitude modulated by a single wave frequency is equivalent to the carrier wave frequency together with two sideband frequencies. Can you should be able to understand the term bandwidth. Acha. Figure 3.3 shows the waveform resulting from the amplitude modulation of a high frequency carrier wave by a signal that consists of a single audio frequency. So this is an AM wave which is obtained by a single carrier wave. Then comes this magical line. When this form is analyzed, how? With what set of equation? What is the type of analysis? What kind of equipment are we going to use? Or there is some way of analyzing this wave which is not shared here, which I am not going to tell you because I don't know, I didn't study about it, I'm not supposed to tell you. So somehow we will analyze this wave, and that analysis will result in this. These two waves are not same. Take a very good look at the axis level. They do not represent the exact same wave. They have different axes. Have a good look. On figure 3.3, the axes are displacement versus time, which means this is an actual displacement of the wave versus time. Beautiful. And on figure 3.4, you can say amplitude versus frequency. Amplitude versus frequency essentially means that at which frequency you're going to have the highest amplitude, which means that precisely, which means in another way that amplitude is very much relevant to intensity or the energy content of a certain wave. So amplitude versus frequency essentially mean that at which frequency you're going to have the highest amount of energy, or you will have the loudest slash brightest slash more energetic in the more highest intensity wave of the whole thing. So whenever we'll analyze this way, figure 3.3, we'll be ending up with a wave like this. This is basically what they're saying over here, that you should understand by analysis of this amplitude modulated wave, we get, if we plot now a graph of amplitude versus frequency, we come up with a graph like this, where the carrier wave gives us the highest amplitude, or which represents itself to have the highest amount of energy content, and we have two sideband frequencies. One sideband frequency is the carrier frequency plus the audio frequency, FC plus FA. The other one is FC minus FA. So here's the part that I want you to understand. If you try to recall that, let's say if this wave has a frequency of, let's say, 100 hertz, and this wave has a frequency of 10 hertz, then together the merging, this wave still has a frequency of 100 hertz, but it has certain variation of amplitude, because in amplitude modulation we don't mess up the carrier waves frequency, we mess up the carrier waves, mess with the carrier waves amplitude. So when we will do the analysis, this will give us a certain amplitude versus frequency graph where the 100 hertz frequency carrier wave will have the highest amplitude. We will have another sideband of 110 hertz. We will have another frequency, another sideband of 90 hertz. So this will be FC plus FA and FC minus FA, and this will be the total meaning of the word bandwidth. Here comes the bottom line. The center frequency FC is that of the high frequency carrier wave. The other two are known as sidebands of the AM waveform, and our correct frequency is FC plus minus FA, where FA is the frequency of the audio signal. The relative amplitude of sidebands and carrier depends on the relative amplitudes of the audio and the carrier waveforms. The relative amplitude of the sidebands and their carrier depends on the relative amplitudes of the audio and the carrier waveforms. If there is no audio frequency signal, there are no sidebands. What it means is that the amplitude variation that we have over here, I mean, which one will have higher amplitude, which will have a low amplitude, is very much related upon what was initially their amplitude values for these two waves. If the information signal has zero amplitude, which basically means that if we do not feed any information signal, if you don't feed any information signal, how the hell is there any modulation? Pretty simple. Let's say you are making a phone call and you are about to talk to someone and you are talking to someone. For whatever reason, for maybe there for 1 second there is a silence, none of you are talking. Your cell phones, towers, everyone is prepared to do the modulation, unmodulation, everything to transfer the whole signal, whole information. But if you are not talking through the microphone, do you have any modulation? You don't, because for that one duration of silence or quiet, you have no information signal available. So you basically have the unmodulated carrier, which is basically transferring through the channel, and you still have communication available, and you are still paying the network because they are willing to do the job, but you are not giving them any job. That's your problem. So that's that. And then comes this part. Bandwidth is the frequency range occupied by the AM waveform. This is equal to 2FA. This is definition of the bandwidth, so you might as well want to highlight this term. To be honest, if they choose not to do that, কারণ এই definition টা আমাদেরকে worksheet করার সময় অনেকবার লিখতে হবে. We'll have to write it a lot of times in the worksheet. So you might as well choose not to do that. Your choice. I really don't mind. Wow. কি বলছিলাম? আচ্ছা, bandwidth is a frequency range occupied by AM waveform. This is equal to 2FA. Now, this is really important for you to understand. Here they say that if it is the frequency range occupied by the AM waveform, in this case, range means the variation from the very highest to the very lowest. If there are multiple values in between, which is not present for this figure, but for other figures there can be, everything belongs within the bandwidth. For example, here they have shown over here, 3.5 is AM waveform at the corresponding frequency spectrum from a voice signal. This is a more realistic scenario that if someone is actually making a voice, there will be moments of quietness, there will be a high figure, there will be high voice and low voice, there will be different type of sounds like hissing and wow, and you know it. I mean, there will be quality of the sound, there will be variations of the, you will not have a pure sine wave. That's what I'm trying to mean. If we do that merging with the carrier wave, if we do the amplitude modulation of that sound wave, we're going to end up, and then if we're going to end up with a figure like this, then if we do that analysis and we try to get the amplitude versus frequency graph, we're going to get a situation like this. We're going to have a center frequency which is going to be pretty high, and it's going to look like this. Now, if you ask me, where did this shape come from? What is the reason for this shape? I honestly don't have the answer for this. This shape, which looks a bit like normal distribution, but not so much. This shape comes from the process of the analysis by which they obtained this one from this one. So I cannot tell you where did this shape come from. You will never be asked why this shape is like this, but one thing you should understand that this shape should be identical on both sides, or in other words, this graph should be bisymmetric about the FC line, because whatever the variations that you get over here, it will be affecting the bandwidth part as FC plus minus FA. So if you have a FC plus 10 hertz over here, you'll have FC minus 10 hertz over here. If you have FC plus 100 hertz over here, you'll have FC minus 100 hertz over here as well. So you'll have this graph would be bisymmetric about the FC line, and whatever the shape that you have on the right, so it will be bisymmetric. You understand what bisymmetric is, and the total bandwidth is the total frequency covered by the full bandwidth is the total frequency range occupied by the AM waveform, which means it is the difference of the maximum frequency bandwidth and the minimum frequency bandwidth. Which means if this is the here you have the maximum and here you have the minimum, this wave frequency covered from within this much to range. So the bandwidth will be all of it, not only one single value. If you have a single value, then it's 2FA. That's pretty simple to work with. But if you have multiple values, you have to choose from the very starting to the very end of the total frequency range. That's basically what we mean by bandwidth. For most part of your syllabus, for most part of your mathematical working, you don't have to deal with these graphs. This is for mostly for idea generation, but sometimes they can show up. For most parts, you will have to deal with these single frequency graphs and do real mathematical calculations about them. I'll take questions right now. If you have any question, please ask me.
So sir, আপনি কি সাইড ব্যান্ডের ওই পার্টটুকু আরেকবার বলতে পারবেন? I really didn't understand যে ওই জিনিসটা কেমনে like it just popped in.
How these sidebands came into existence is not shared in your syllabus. It says that when this waveform is analyzed, it is seen to be composed of the sum of three waves of three separate frequencies. So how did the analysis of this wave give us the carrier wave sidebands individually different? That analysis process is not shared with us or not shared in your syllabus. I did not study about this, but I know I did come across certain literature and other parts that I could study about it, but chose not to because I'm lazy. But if you are interested, I can guide you there. But the point is that analysis of this AM wave, AM amplitude modulated wave, gives us these things. These sidebands come from a certain way of analysis. Now, I don't know what that is, but this is the outcome that we have to know. Sidebands are basically this thing. If you just have a look at this one, this should make sense. That sidebands have the value, individual sidebands have the value of FC plus minus FA. So if your original audio signal consists of a single audio frequency, then we're going to have two exclusive sidebands, not a range of frequencies. So you're going to have one on the higher side, one on the lower side. So FC plus FA is one, FC minus FA is the other one, and that's basically it. But if you have a range of frequency in your original audio frequency, which is the more realistic case like this, that frequency can have variation. So it will be covering a lot of range over, a lot of locations over here, more or less, and similarly on the both sides. Your exact question is not answered because that process of how this came into this is not explained in the syllabus.
And sir, এই যে সাইড ব্যান্ডের অ্যামপ্লিটিউডটা কেন ক্যারিয়ারের থেকে অলওয়েজ কম হবে?
No, it doesn't have to be less. It can be more than carrier if within our modulation, if we choose that the modulated carrier has a smaller frequency, smaller amplitude, and the inference signal has a higher amplitude. If we set up in that manner, then it is possible that the carrier wave can have a higher amplitude. The amplitude of these three bars, or the height of these three bars, is relevant to their initial amplitude values. This is what is said over here. The relative amplitude of the sidebands and the carrier depends on the relative amplitudes of the audio and the carrier waveforms. Which means the amplitude variation that you see over here, this variation will be directly reflected from the variation of the original sources. These things are not done to any scale because on the y-axis you don't see any scale value. So what they are assuming that if this carrier wave had a maximum amplitude of, let's say, maybe 10 volt, maybe this information signal had a carrier value of, let's say, 5 volt. So you have about nearly half the height of the carrier versus sideband. That's what they're assuming. But if you choose both of these to be of exactly same amplitude, for example, if this is 10 volt, this is also 10 volt, then you will have all of these three bars coming up at the same level. So how high these bars are going to be is very much relevant to how high they used to be to begin with. Bucho.
জি স্যার।
Okay. Anything else, anyone? Yeah, Mugdha, go ahead.
Sir, AM modulation, we are supposed to vary the amplitude with the information signal. কিন্তু এখানে তো frequency variation দেখাচ্ছে. As in, I didn't get this part.
No. The primary modulated wave, which comes from the process of modulation, that only has one frequency but different amplitude. This is the modulated wave. When this modulated wave was analyzed, then we came to have this thing. This is not a continuous variation of frequency. a frequency modulated wave would look like this, where you have a continuous variation of frequency over the time. This is not a continuous variation of the frequency. This is just showing us that analysis of this wave will result in 3 individual waves, which basically means that whenever we'll reach, I mean, in other words, I can say that whenever this wave will be received on the receiving end, whenever this wave will be received on the receiving end, and then we'll try to extract out the information signal out of the carrier signal, then we will come across this scenario. We will not exactly get out the carrier wave frequency. I mean, if we try to break it down back into this thing, I mean, so if we might wonder that why is that even necessary? Let me give a very simple idea of how this works. I mean, let's say I'm a singer singing in a radio station. I'm singing through a microphone. My voice information, which is going to be this one, but much varied, will be taken out or taken from the wires, added with the carrier wave frequency of the radio station, and merged into their preferred variation. Let's say with this gonna merge AM, so it's gonna make this, and then from the antenna of the radio station, it will be sent broadcasted over a long distance. Let's say another person, let's say one of my students is trying to listen to this music, although it's very bad, but they're still trying to listen to this music for reasons unknown, and then they tune their radio to that carrier wave frequency. So in their antenna, they'll be receiving this one. But from this one, this is basically not audio signal. For hearing the actual music, you have to make this thing from this thing. So you have to somehow subtract this part from this thing so that you are left with this one, because this plus this equals to this.
Yes,
Somehow
sir.
we have to make this thing available out of this thing. So whenever this subtraction is done, or whenever this analysis part is done, that usually give us 3 individual frequency of sidebands. So we're going to get the primary carrier wave, and we're going to give 2 sideband frequencies, one slightly higher and one slightly lower. And somehow these 2 things are utilized together to make this original wave. So at which part of the analysis do we have these 2 sidebands? That is not necessarily told us, because the basis process of analysis is not said. This is amplitude modulation, and when this amplitude modulation is analyzed further, we get this kind of variation where we have 3 individual frequencies. This is not frequency modulation. Frequency modulation would mean a continuous variation of frequency based upon the amplitude of the information signal. I'll say it again. Listen to every single word. Frequency modulation means a continuous variation of the frequency of the carrier wave depending upon the amplitude of the information signal. But that's not what is happening here. This is secondary analysis of the amplitude modulated wave, and that gives us 3 different frequency presence.
Sir, মানে analysis করার পর we get 3 different signals through which we can calculate the original information signal from.
Precisely.
Okay, thank you, sir.
Sure. The reason they picked up this halfway information from a series of output processing is that they wanted to introduce you to the term bandwidth. This is the graph which gives us that idea of bandwidth. That's why they picked up this specific part on the output processing part. From there are a range of processes that happens. We're going to see some of them later on. Okay. Then comes this paragraph. This is actually good. Acha. Have a look at the heading. Candidates should be able to demonstrate awareness of the relative advantages of AM and FM transmissions. I'm going to talk a lot of stuff to make you understand these 1, 2, 3, 4, 5, 6 paragraphs. But you don't essentially have to remember all of this. But you have to somehow remember a summary of this whole thing. Sometimes this question do come up for 4 or 5 marks that mention 5 advantages, disadvantages of FM and AM with respect to each other, blah, blah, blah. Before I start this heading, I'd like to show you this table. Have a look over here. The typical frequency range that we use for communication purposes that is divided internationally by all the communication channel people who pioneered this technology by 3 different sections. Frequencies lower than 3 megahertz are say surface waves. 3 megahertz to 30 megahertz, they are called the sky wave. Greater than 30 megahertz are said to be space waves. Surface waves were the first set of communication that we human beings achieved for long distance wireless communication. To achieve this, we precisely need land towers. One tower to another tower to another tower, it can communication only that way. Has a range of up to 1000 kilometers. Skywave was the next thing that we achieved when we could find out that we can have the radio signal or the information signal or electromagnetic wave reflected off the ionosphere. So at this point, I mean, this was developed within the time when satellite technology was not so much developed, which is really developed right now. So we human beings used the reflection from the ionosphere. We basically use the ionosphere as like a mirror for the electromagnetic wave, and would send from one location of the Earth, and that reflection of the ionosphere would give us transmission over a large area. There are certain problems for this communication process because whenever the reflection will be received from the ionosphere reflection, it will be very weak. So your receiving components had to be really strong to pick up that signal, and also there will be a pretty large lag. Lag means the time instance from when the signal is sent from the ground station to the time instance when it is received by the radio signal on another ground station. This would require a significant amount of time because the signal has to travel all the way to the ionosphere, then reflect back to the ionosphere, to the ground. So the physical distance covered, even though it's electromagnetic wave, is actually quite large. So it would take some significant amount of time for that to achieve, for us to achieve that. And then with the space wave, which is divided into 30 megahertz, we want the 30 megahertz. This is line of sight, including cellular communication. So this is the most common frequency range that we use right now. To be honest, all the recent modern communication that we can see right now that we take for granted, they use this frequency. Even Wi-Fi routers as well. Actually, just a second. All right. These 3 basic divisions are once again subdivided into other smaller parts for easier description of the channels, which is shown on the lower figure 3.12. Have a look. We have multiple different names for different effective ranges of these frequencies. You don't have to memorize this table. I'm showing you this table for a certain reference, which you'll be using for the earlier part. We have long wave radio, medium wave radio, short wave radio, frequency modulated radio, TV broadcast, then we have microwave or satellite. So this whole range below 33 megahertz. So you can see that the starting frequency that we're choosing to do radio communication is from 30 kilohertz. If you wonder why 30 kilohertz, why not any smaller? Because 20 kilohertz is basically the last threshold for our audible range. If we choose a frequency wave that is within 20 kilohertz, then the carrier wave and the information signal they will fall onto each other. We don't want that to happen. So we're choosing a bit higher side from the radio frequency. This is the so these are the different frequency ranges that we have for the surface wave, sky wave, and space wave, which are divided into subdivisions. এই ডিভিশনের সবগুলো ডেনোমিনেশন গুলো তোমাদের মনে রাখা লাগবে না, বাট উইল বি ইউজিং দিস ইনফরমেশন ফর দ্যাট প্যারাগ্রাফ। সো ওটাতে ব্যাক করি এই জিনিসটা, সেখানে কিছু ইনফরমেশন আছে, দরকার ইনফরমেশন আছে যেগুলো মনে রাখা দরকার। But এখানে কিছু information আছে. These are all theoretical stuffs, but I'll help you understand them better. Don't worry about that. এখানে জিনিসটা বলছে, first paragraph খেয়াল করো. An real receiving electromagnetic waves cannot distinguish between a genuine radio signal and say the interfering radiation from the ignition system of a passing motorbike. The reason they picked up this exact example, the interfering radiation from a ignition system of a passing motorbike, is that the frequency of this sound can be within the same range or can be exactly same as a certain value of a radio signal. So if you feed both of these sounds together to a receiving antenna, that antenna by its own virtue does not have the capability to distinguish these two sounds. It would consider both of them to be a combined sound and convert both of them into output. If the radio signal is AM, the interference would be considered to be part of the modulation. So what this means that as the sound will travel from one location to another location, in the way of traveling, it can become interfered with a lot of sounding sounds like the motorbike ignition system or other sources that produces similar frequency of that carrier signal. And all of those individual variations would get added to the modulated wave. And when it will be received onto the receiving signal, that receiving antenna would not be able to distinguish between which was the actual sound coming from the antenna and which is the actual noise that got added within the communication channel. So that's what this line says, that if the radio signal is AM, the interference would be considered to be part of the modulation, and so it becomes audible in the output produced by the receiver. If, however, the radio signal is FM, the interference will not be picked up by the receiver because it is only variations in frequency that are important, not variations in amplitude. This is very important information that you have to understand. Whenever interference happen, superposition interference happen of two different waves, the property of the wave that undergoes change by interference is the amplitude of the wave, not frequency. Multiple waves, let's say two waves of same frequency merge together to produce a new set of amplitudes / displacements. That is what we understand by interference. So in the process of interference, you have a change of amplitude, not the frequency. So even if a certain frequency modulated wave, which basically looks like this, has some ups and downs in its individual amplitude values, where it picked up some noise means it got interfered by similar frequency wave and had a variation of its amplitude. This would not cause any significant problem on the receiving side because the receiving side is not going to reproduce the original audio signal by means of variation of amplitude. It will look up for the variation of frequencies, and the variation of frequencies will remain intact because frequencies are not affected by interference, amplitude is affected by interference. So the frequency variation would remain intact. So this is why it says further in this paragraph that if, however, the radio signal is FM, the interference will not be picked up by the receiver because it is only variation in frequency that are important, not variations in amplitude. Thus, the quality in terms of interference of AM reception is generally poorer than that of FM. It means AM signals are more prone towards picking up noises in the communication pathway, and they are likely to give us more noisy output. Whereas frequency modulation waves don't have that property because of the inherent structure, because they're handled with the variation of frequency change, so amplitude variation does not pose any problem. এটা হচ্ছে একটা প্যারাগ্রাফ। সো এই প্যারাগ্রাফ থেকে আমরা বুঝলাম যে in terms of noise pickup thing, in terms of noisy signal, AM outputs are generally poorer than the FM. মানে হচ্ছে, simply put, if you tune in into a FM station, you are likely to hear a more clear crystal sound compared to an AM. If you tune into an AM station, you might hear a lot of static kind of sound additional to the actual audio signal that you are expecting to receive. Same paragraph. On the long wave and medium wave bands, so we are now discussing, limiting our discussion for only these two parts. The bandwidth of an AM radio station is 9 kilohertz. Now, here is the deal. This is an information that is given to you. On the long wave and the medium wave bands, the bandwidth on an AM radio station is 9 kilohertz. If you wonder why 9 kilohertz and why cannot be more than that, the reason is for the sake of easier licensing and similar type of structure of all the radio stations, all the transmission processes around the world, unless there are some specific variation, for example, NSA or some secret radio channels of Navy SEALs like those, the regular business communication channels, they have a basic regulation around the world. So everyone follows that basic regulation so that there is no complications, so that equipments can be produced by a specific type, so that you can have replaceable equipments, and so on and so forth. So having a specific regulation has a lot of advantages, which you might as well understand that now we have USB 3 and USB 2 chargers for Android phones. But not a lot ago, we had a lot, let's say 6 to 7 years ago, we had a lot of different versions of chargers. Samsung phones had one type of chargers, Sony Ericsson phones had other type of chargers, Nokia phones had chicken pin or mota pin chargers, and the Android phones used to have these USB 2 chargers. So there were a lot of variations, but currently the number of outlets for the chargers have reduced significantly because the entire world has somehow converged towards choosing USB output. And these USB outputs can be used for a lot of other charging devices, for example, rechargeable batteries, your basic stuffs. I mean, this has sort of become the industry standard because it is easier to manufacture components in that way. So this line is basically a representation of that thing, that on the long wave and medium wave bands, the bandwidth of an AM radio station is 9 kilohertz. Now recall, what did we mean by bandwidth? Bandwidth means the maximum and minimum range difference of a certain radio station. So if the bandwidth of a certain station is 9 kilohertz, the original FA, bandwidth means 2FA, remember, bandwidth means 2FA. So if 2FA equals to 9 kilohertz, it means FA equals to 4.5 kilohertz. FA equals to 4.5 kilohertz. Now comes the information. This means that the maximum audio frequency that can be broadcast is 4.5 kilohertz. You cannot achieve more than 4.5 kilohertz because if you want to achieve more than 4.5 kilohertz, you need this whole bandwidth to be more than 9 because you have 4.5 on one side, 4.5 kilohertz on other side. Together you're going to have 9 kilohertz. So one side of the carrier wave frequency you can have 4.5 kilohertz only. This frequency is well below the highest frequency audible to human ear, about 15 kilohertz, and therefore such broadcasts lack higher frequencies and thus quality. Let me elaborate what this means. Our human audible range goes from 20 hertz to 20 kilohertz. This is a very inclusive range, means the possible lowest frequency we as human species could hear is 20 hertz, and the possible maximum we could hear is 20 kilohertz. Typically, babies or young children, they can hear the highest frequencies, I mean more than close to 20 kilohertz when their hearing system or audio systems are not so old, they are not damaged by loud sounds or overutilization of headphones or such. They can hear the high frequencies. As people get older, our capability to hear much high frequency sounds get lower. So a more practical threshold for the highest audible frequency for human beings is 15 kilohertz, practical threshold. So that's why they have used the term over 15 kilohertz. So what I'm trying to mean is that a regular human being can hear from, let's say, 20 hertz to 15 kilohertz. This is the total range of variation of frequency variation that we human beings can hear and decipher in our brain. If we use AM, then for these two long wave and the medium wave bands, our transmission frequency variation for the information signal is limited up to 4.5 kilohertz. So what this essentially is telling us that we could hear, I'm showing you over here just to give you a bit of a understanding. This figure that I want to draw, you don't have to understand. We could hear from 20 hertz to practically up to, let's say, 15 kilohertz. But in that channel, we could transfer from 20 hertz up to 4.5 kilohertz. So the radio channel could use only this much or only this part of our audible range. So a huge portion over here is remaining underutilized. We cannot transmit audio sounds of frequencies more than 4.5 kilohertz through the long wave and medium wave band channels. This makes so, and therefore such broadcasts lack higher frequencies and thus quality. It means through these channels, because of the limitation of the bandwidth, we cannot practically broadcast higher frequency sound. What this means that if, let's say, and let me give you an idea. Let's say you want to transmit some news channel over an AM station, it will work just fine because basic human voice covers within 4 and 5 kilohertz. News, okay. You want to transfer some bhashan, okay. But if you want to transfer an orchestra through an AM channel, you will go through some trouble because within an orchestra you have a lot of equipments producing a lot of different range of frequency of sounds. You have from very low bass to very high frequency clarinet music. Clarinet is a type of flute which makes very high frequency sound. Or you have the high pitched tones of a violin, for example, or the high tones of the piano, or other equipments, you name it. So there will be a mixture of a lot of high frequency sound. Within an AM channel of long wave through medium wave, we can transfer up to maximum 4.5 kilohertz of original sound. Any sound that has its frequency above 4.5 kilohertz, we cannot input this within this AM station, which means our sound that we are capable to transfer will not be as varied as it could be, or would not be as shruti madhur as it could have been because of the lack of space of frequency variation. That's why they are saying that this is why AM channels lack higher frequency and thus quality. Thus quality means a higher quality in a sound means what? You have a huge amount of variation of sounds. So you have high frequency, low frequency, all mixed up together, giving a huge variation of sound, which basically feels to be more pleasing to our ear. But in an AM station, you cannot have that. You will have up to 4.5 kilohertz. So you might as well have tabla, drum, harmonium. You might actually have basic voice, but you might not have super high frequency sounds or actual orchestra. They are not going to be very pleasing to hear over this thing. এই পার্টটা বুঝা গেছে কিনা about the limitation of usable frequency range. Any question about the second paragraph, kids? Raiki, any question no লিখছো নাকি বুঝা গেছে কিনা তেন লিখছো? আচ্ছা. So since there is no question, I'm moving on to the third paragraph. Third paragraph টা দেখো. This one says on the very high frequency VHF wave band, the bandwidth of an FM radio station is about 200 kilohertz. This is a given information. Once again, like I said, for the standard behavior is that if some radio station operates in the VHF frequency, the bandwidth of an FM radio station is about 200 kilohertz, and the maximum audio frequency broadcast is 15 kilohertz. Maximum audio frequency broadcast 15 kilohertz মানে হচ্ছে FA এর maximum value হচ্ছে 15 kilohertz, মানে এইটুক হচ্ছে 15 kilohertz, তার মানে টোটাল ব্যান্ডউইথ হবে হচ্ছে 30 kilohertz. So on the VHF wave band, if there is an FM stereo station which typically operates with a carrier wave signal of 200 kilohertz, it has a maximum audio frequency of 15 kilohertz. The quality of the music received on AM is poorer than that of FM. In that case, the quality of music received on AM is poorer than that of FM, but in this case on the basis of bandwidth. These two paragraphs, 2 and 3, basically gives us one single information that AM is poorer, FM is better in terms of bandwidth because FM can cover the total practical range of audible frequency for human, whereas AM cannot cover the total practical range of audible frequency for the human beings. So এই paragraph basically all the information na, they pretty much means that it gives the same information. This one talks about the AM limitation, this one gives information about the FM superiority, but together they make up one point that AM is poorer in terms of quality of output sound because it covers a smaller bandwidth, whereas FM is better because it covers a bigger bandwidth. That's the total gist of these two paragraphs. The first paragraph was a different thing. The first paragraph said that AM picks up noise from the communication channel more effectively, which cannot be distinguished on the receiving end, which means any noise picked up in the communication channel will be played as output on the output side, whereas FM might pick up noise which is going to affect the amplitude, but since amplitude variation is not the thing that we're going to judge, we're going to judge the frequency variation. So using FM will not be affected by that interference. So FM gives us more noiseless sound or more perfect sound, whereas AM gives us more noisy sound. Static is more. So এই তিনটা প্যারাগ্রাফ গেল। ফোর্থ প্যারাগ্রাফ দেখো, the LW waveband occupies a region of the electromagnetic spectrum from 30 kilohertz to 300 kilohertz. This is for the LW. So we just showed over here. 30 kilohertz to 300 kilohertz. The LW waveband occupies a region of electromagnetic spectrum from 30 kilohertz to 300 kilohertz. The number of separate AM radio stations that could share this waveband is theoretically 30. কোথায় আসলো বলতেছি 30 kilohertz থেকে 300 kilohertz পর্যন্ত total available range of frequency হচ্ছে 270 kilohertz. If you do the subtraction, basic subtraction, how many individual AM radio station can use this amount of range within the same geographic region, within the same alaka? That is theoretically 270 divided by 9 equals to 30. If you think 270, this is the subtraction result of these two. So you have a total value of 270 kilohertz to be that you can sell. Let's say you own the BRTC. So as a country, you can sell a total range of 270 kilohertz. Each AM radio station requires a bandwidth of 9 kilohertz, which you have seen in the earlier paragraph that the individual radio station এর জন্য maximum audio frequency broadcast is 4.5 kilohertz. So 4.5 kilohertz যদি FL value হয় তাহলে 2FA value হচ্ছে 9 kilohertz. So each AM station requires a bandwidth of 9 kilohertz. So theoretically this 270 kilohertz of space মানে physical space না, bandwidth space that can be occupied by 30 radio stations simultaneously, which means that let's say you're going to send one radio station from 30 kilohertz to 39 kilohertz. This will belong to one radio station. Another one can be sold from 39 to 48. Another one can be sold from 48 to 57. So you're going to sell 9 kilohertz worth of frequency range to individual radio stations, radio companies, and theoretically within a given amount of space, there can be 30 individual radio stations that can operate, if all of which are operating within the LW waveband. So that's one thing. However, the number of separate FM station would be only 270 by 200 equals to 1. The math looks wrong, but I'll tell you why this is not wrong. 270 করতে আসছে খেয়াল, 270 হচ্ছে ডিফারেন্স থেকে। If you want to operate an FM station within the same 30 kilohertz to 300 kilohertz range, you have an available radio bandwidth frequency of 270 kilohertz. One FM station on the very high frequency waveband, the bandwidth of the FM radio station uses about 200 kilohertz. So FM stationer frequency waveband হচ্ছে the bandwidth of an FM radio station is about 200 kilohertz. So bandwidth মানে হচ্ছে the total of this thing is 200 kilohertz. So একটা FM স্টেশনে অপারেট করার জন্য একারই লাগবে হচ্ছে টোটাল 200 kilohertz on both side. সো একটা 270 কিলোহার্টজ রেঞ্জের মধ্যে তুমি কয়টা 200 কিলোহার্টজ এফএম স্টেশনকে অ্যাকোমোডেট করতে পারবা? তুমি যে পাশ থেকে শুরু করো না কেন, ইউ ক্যানট অ্যাকোমোডেট মোর দেন ওয়ান, because if you want to accommodate more than one, there will be some overlapping regions. Overlapping means একজনের সিগন্যাল আরেকজন যে কোনো সময় ইন্টারফেয়ার করে খাই দিতে পারবে. There will be mess up in the process of communication process. So we don't want that to happen. So for successful communication process, we can sell or we can operate a maximum of one FM station within the 30 kilohertz to 300 kilohertz range, because the bandwidth requirement for one FM station is 200 kilohertz. So 270 divided by 200 equals to 1. In this case, this one means maximum 1. You can have 1 point something, but 1 point something to our fractional reduction hoite parbe na. So that's why they have reduced only 1. So the last sentence says, so more AM's radio stations than FM radio stations can share any waveband, For this reason, FM is used only at frequencies in excess of 1 megahertz. So যদি আমরা FM stations কে এই রেঞ্জে ইউজ করতে চাই, তার ব্যান্ডউইথ হতে হতে 200 কিলোহার্টজ। সো একটা ফিজিক্যাল জিওগ্রাফিক রিজনে একটার বেশি FM স্টেশন অপারেট করতে পারতো না। This is why typically FM stations are not used in this range. FM stations have their carrier waves in excess of 1 megahertz. To be honest, if you try to tune up through your cell phones, the first radio station that you might get, it starts from 85 megahertz. Your cell phone will try to tune in the radio stations from 85 megahertz, and it is going to go all the way up to 120 or 125 এই পর্যন্ত যায়. So around the globe, all the FM stations currently operate from 85 megahertz all the way up to 125 megahertz. So in this case, they are saying in excess of 1 megahertz. This is the typical preference, but practically the preferred radio frequency values, carrier frequency values for the FM stations starts from about 85 megahertz. Now, one thing it is pretty important that you might find that the radio station that we have in our country, one is at 85.0 megahertz, then you have 85.4, then you have 85.8. Do you know this thing that we have a variation of 0.4 megahertz? Anyone? Did anyone see that? Okay, Raya is saying that she does. What I'm trying to mean, so what I'm trying to mean is that if you try to tune in, you will find that you might find a radio station at 85.0 megahertz, then you might find another one at 85.4, then you might find 85.8, then you might find 86.2. It goes on like that. The smallest division between two radio stations is actually 0.4 megahertz. This is because, like I said, that each of the station has a bandwidth of 200 kilohertz. So that is 0.2 megahertz. So this one plus this is the bandwidth. So this one can have a variation from here through here. So we have a total of 100 kilohertz over here. I'm going to write 0.1 megahertz, 0.1 megahertz on one side and 0.1 megahertz on the other side. So the total maximum frequency of this radio station 85.4 can go up to 85.5. The lowest it can cover is 85.3. Whereas this one can have a highest of 85.1 and this one can have a lowest of 84.9. That's the variation that we're going to work with, because 200 kilohertz was the bandwidth, which means half of it was in one side. This leaves us a forbidden gap kind of thing. এই রিজনটাতে প্র্যাকটিক্যালি কেউ অপারেট করতেছে না। The government does not sell them to be continuous because government prefers to keep some convenient gap in between so that they might use these things for their own personal communication channel in places, like I said, NSA or other people or their police radio walkie-talkie, those kind of channels, or Government might sell these things later on to some other communication channel if required. But typically, this 200 megabyte, so this lowest value was 85.1, and this is 85.3. So this is 85.3. So you have a difference of about 0.2 megahertz, or you have a difference of, you have the space to accommodate another radio station over here. But government doesn't sell that space because, first of all, we don't want marginal overlap that can lead to some problem. That might, I'm not sure exactly what, but that might lead to some problem because we will have overlapping boundary lines. But this, having this gap makes the country to be able to use those channels in cases of their own requirement. ঠিক আছে? The Wi-Fi communication that we use usually uses even a higher frequency value. I mean, এটা আমি exact value টা জানি না. Might as well be a good time to look it up. Oh, Wi-Fi is work with a frequency variation of, this is the this frequency means this is the carrier frequency. Wi-Fi works from 2.4 gigahertz to 5 gigahertz. So that's a lot. And now the higher your frequency is, the more variation you can have per second. So going to much higher frequency basically means you have a basic way to do faster communication. So all these, 3G, 5G, 3.5G means that these things were going higher. Anyway, so this is the part that we have over here. So the paragraph, the significance of this fourth paragraph is that if we use AM radio stations within the LW wave band, 30 kilohertz to 300 kilohertz, theoretically you can operate 30 individual AM radio stations within the same geographic space. But because the FM radio station has have a bandwidth of 200 kilohertz, theoretically we could only operate only one. Yes, the difference between each channel, between two consecutive channels, is 0.4 megahertz. That is for the carrier wave. Then again, they would have an individual bandwidth of something, so the maximum minimum would be a bit more or less than that. মুজু কি বলছি বুঝছো?
Yes, sir.
আচ্ছা, so এটা গেল হচ্ছে এটা. So according to this paragraph basically tells us that this paragraph is actually an advantage for the AM. The advantage is that if you use AM for the LW, you can use a lot of radio stations. If you want to use FM for the LW, you can use only one radio station. So in this case, you can have more transmission capability by a lot of radio stations. So this paragraph is basically representing an advantage of the AM over FM. Fifth paragraph, this one. The AM transmissions on the LW, MW, and SW wavebands are propagated very large distances, so broadcasts can be made to a very large area from only one transmitter. The AM transmissions can, for all of these three regions, LW, MW, or SW, they can be propagated very large distances so that the broadcast can be made to a very large area from only one transmitter. FM transmissions have a range of only about 30 kilometers by line of sight. So, let me finish that out. To broadcast to a large area, many FM stereo transmitters are required. It is therefore much cheaper and simpler to broadcast by AM than FM. What their meaning is that if you use an AM station, AM transmission process for a radio, you can use one AM antenna, one radio transmission center to cover a huge area because it has a really large amount of range. The range is even not mentioned, very large distances. Whereas a typical FM station can cover up to 30 kilometers of space within line of sight. Within line of sight. So if you want to cover a large amount of space, you require a lot of individual antennas for all the radio stations. So operating a radio station which works with AM is cheaper because you would require fewer transmission centers. But operating an FM would be costlier because you'd require you would require one new radio station for every 30-kilometer radius of circular area and onwards. But if there are physical, there are more. If there are more, more line of sight obstacles, you would have to. You might require more. So it is preferable to have them attached on top of tall buildings so that you have line of sight communication to most of the people. If you place it on top of a small building, then you'll be blocked by a large building anywhere on the side, and all the people behind that building will not have good coverage. So that's another thing. So in this paragraph represents a benefit of AM over FM, that FM is costlier in terms of requirement of towers to coverage a large area, whereas AM is cheaper. The last paragraph says AM transmissions and receivers are electronically simpler and cheaper, and they also occupy a much smaller bandwidth than those of FM, which means the devices you're going to buy for AM, those devices are even cheaper compared to FM. So it's another advantage of AM. FM equipments are electronically complicated. You need a lot of electronics and a complicated circuit diagrams to build them, and also they are costlier. So এই হচ্ছে altogether variation. I just explain these parts. কোশ্চেন আসলে আমরা কিভাবে বুঝে লিখতে পারবো সেটা আমরা ওয়ার্কশিট দেখার সময় দেখবো। আপাতত আমি ওই পার্টটাতে যাচ্ছি না। I would like to show you some mathematical part for today's class. This was my primary goal, so I really want to jump into these things. But আচ্ছা এগুলো আমি একটু ছোট ছোট করে বলে যাই। There are a lot of information over here. I'd like you to read it in your own time, but let me just explain what is happening. If you have an analog signal which is not converted into digital signal means zeros and ones. Analog signal means basically how a signal produced. For example, the signal that we see on a cathode oscilloscope is basically an analog signal. You are putting in some signal in the microphone or through your signal generator. Whatever the variation that you're feeding in, that is shown in its exact continuous variable. So analog signal is basically continuous variable. There's a continuous change of the signal variation. Whereas digital signal is a discrete variable. You have either zeros or one. You don't have anything in between. You don't have negative values. You have 0 voltages or 1 voltages. That's it. So analog signal, if you transmit over the conventional channel, two things will happen. One, you will lose voltage. You can see that the amplitudes over here have become smaller, and also it will pick up noise. The noise pickup is shown by this gizzy line. You can see that there are some, okay, wait on. You can see there are some ups and downs over here. These ups and downs are the noise or the physical interference picked up by the signal as it was traveling through the transmission channel. Whenever it will be received, you can see over here, this is a repeater amplifier. Repeater amplifier means it will pick up the signal, simply amplify it. If you wonder how, we have seen it for the op-amp. You send in a small voltage, it comes out as a proportionally large voltage. So we can use a repeater amplifier, and this will amplify the signal, including the noise. So whenever you repeat this amplifier, you're going to have a similar shape of the original signal, but all the noise that it picked up in between, they will be incorporated as well. You cannot get these things out. Whereas if you have a digital signal processing, you send the original digital signal, which is a clean signal coming out from your antenna, fresh antenna. So fresh signal, no problem yet. Transmitted over long distances, the voltage becomes smaller, and each of the values where it is not zero, these things pick up the problem. You might wonder that why is there only zigzag on the horizontal lines and not on the vertical lines. You have to understand, these vertical lines represent zero time frame, the time instance where the voltage changed from 1 to 0. So you cannot have horizontal zigzag. That would be going back in time. So it's actually not logical. So this is just a basic variation. So the same thing is happening over here. All the value of the voltages are picking up noise, and we have the ones and zeros. But whenever it will be picked up by the receiving end, we have a regenerator over here. What the regenerator does, it does not identically amplify this thing. The regenerator circuit or regenerator equipment observes the received signal and assigns its own voltage onto a signal. So if this value is let's say more than 1, it applies its own personal full voltage over here for the same duration. And whenever it is close to 0, then it applies perfectly 0. So this is sort of like a comparator circuit that, let's say we're gonna set this threshold at, let's say we're assuming for the amount of transmission path that we have, the amount of noise that we can pick up, let's assume that this 0 signal can have a maximum value of, let's say, 0.1. So it cannot be more than 0.1. So let's say we're gonna set up the op amp to have a lower threshold of 0.11. 0.11 means any voltage value that is higher than 0.11 will be given the full output voltage. Any voltage input that is lower than 0.11 will be given 0. We can design an op amp circuit like that. Basically, a regenerator circuit works in that manner. It takes the input from the received signal and recreates the entire signal, regenerates the entire signal from its own voltage supply. So this basically makes the entire noise pickup gone. How is having many different transmitters operating in a specific frequency range advantageous? Oh, no. Many transmitters should not operate with the same bandwidth in the same region, because if you have the same bandwidth of multiple radio stations, they interfere with each other's signals. Having many transmitters within the same geographic region is beneficial because you can transmit a lot of different programs to two different channels. For example, so you can have one channel dedicated to religion. You can have one radio channel dedicated to atheism. You can have one radio channel dedicated to music. One radio channel dedicated to, let's say, for the government, pro-government, and one for the anti-government. So you can have a lot of different radio channels who have specialization for different things. So you can have a lot of information delivered to the customers. What your customers are going to hear, that is their choice. But you can have a lot of communication channels. This is basically like having a menu in the restaurant. I mean, if you have only one radio station, you basically have one item in your restaurant. And if you have a lot of radio stations in a certain working in a certain region, you have a lot of item in your restaurant. Something like that, if that makes sense.
So we can, sir, we can accommodate more content within a smaller range, as in more different transmitters which can transmit different content.
Yes.
Yes, sir, got it. Thank you, sir.
Sure, no problem. Sorry. So এই পার্টটা বুঝা গেছে কিনা যে ডিজিটাল সিগন্যালের সুবিধাটা হচ্ছে any single time the digital signal has to be sent on to the next version. This is actually a common thing that whenever we have signals traveling from one place to another place, beyond a certain distance, we need to have energizer station. I'm making this word up. Energizer station basically means that it should pick up the weak signal, make it stronger, and then it send it back again to the next station. Because if you don't make it stronger, it is possible that that signal will become so weak that that eventually at the final receiving station, it would be indistinguishable from the noise. So that's what we want. So the benefit of analog digital signal is that every single time it is regenerated, you are cutting off the noise picked up to the earlier channel, and then this process can work indefinitely with respect to the scale for how much you want to have it happen. Whereas for the analog signal or analog channel, you cannot cut off the noise. This is why analog channels, analog communication channels, which are basically physical material-based communication channels, for example, wires or something like that. These communication channels, coaxial wire or wire pair, whatever, these communication channels are not recommended to work over really long distances. For example, if you're operating within a small range, then you can have analog signals and they'll work just fine. But if you're working on a large distance, then a digital signal is definitely more preferred. So if I tell you an example, for example, if you're having a concert, that you want to have the people of the concert in the stadium to enjoy the music. An analog communication channel with wires and everything is perfectly okay. No big deal. You don't have to go for digital. But if you want to live transmit that constant round the globe, an analog channel, wire-based channel is highly not recommended. You preferably have to use digital communication systems so that every single time you receive the data, you can cut off the noise and give the original transmission to the people. So that's what I'm trying to mean for distances. And I'd like to go for this one. This is the key mathematical part for the combination channel part, which I really like. Before I get into this one, some of you might have computer in your O-levels or your A-level syllabus, so some of you might know how to convert digital signals, digital numbers into binary numbers, binary into decimal and blah, blah, blah. Some of you might not. For those of you who do not know how to convert decimals into binary or binary into decimals, you have to first know that. I'll just explain what is happening over here in my own words, then I'm gonna have you read this whole information, and then I'm gonna pick up some information that you would be finding out for me to describe. This is what is happening over here. If we want to convert, to send, if you want to use a digital channel from one place to another place, we need to convert an analog signal into a digital signal, because the way primary signals, in this case, we are considering voice signals for easy understanding. Let's say this is a single frequency voice signal. These things are always a continuous variable. For example, if you think for a tuning fork, it produces a continuous frequency variation, continuous displacement change. So that variation of pressure slash that amplitude variation is a continuous function. Digital signal cannot work with continuous function, because digital signal is all about steps. You have zeros and ones. You have, if you think for decimal numbers as well, then the way integer numbers work, you have 0, you have 1, then 2, then 3, then 4. These are discrete numbers. All the in-between values are not to be considered. If you wonder that, well, what if I want to convert them, then how many would you consider them? Between 1 and 2, there are billions and billions and billions and billions, and like that guy, American ex-president Namki, Donald Trump. So between two different numbers, integer numbers, you can have a lot of individual numbers. So it's impossible to cover all of them. So what we are gonna do, we are not going to consider all the individual continuous values. Rather, we're gonna chop this information into convenient size. Chopping means we're not gonna use all the values. We're gonna use some precise values that we want to deal with. So, and then we're going to recreate the signal based upon those values, which would be somewhat similar of the original signal. So this is the original analog signal, this is the recovered analog signal. You can say they are not essentially same, but they are quite similar. If you wonder they don't look similar at all, I'll tell you that they do look similar, and there are ways to make them look more similar as well. We're going to share those information as well. So our aim is to understand how to make this into this one. How does that happen? What is the magic that we have to do? So first of all, one thing that you have to understand is the word sampling frequency, which is said over here. That is the sampling frequency different? No, it's not defined over here. The word sampling frequency. Sampling frequency means sampling. Actually, let me tell you what the word sampling means. Basically, the word sampling means that you are going to judge a certain thing, variable, not for all of their value, for specific interval. Now, a simple example, one of the primary ways for quality control in any production facility is that you have to choose random component out in the output line and compare them. For example, let's say you are producing, let's assume that you are producing juice in a manufacturing country. Now, what are the, if you want to check whether the production facility is working well or not, you have to do the product checking. Now, if you really want to do product checking for all of the juice packs, you have to practically take out all of the juice packs out of the output side, open them up, take the juice out, measurement all of them. That's basically destroying all the products. You cannot do that. So what you can do, maybe for every 1,000 juice pack, you're going to pick up one, or maybe 100, or maybe 200. It depends upon the factory recommendation. You can pick up one juice pack, then open it up. You find out exactly how much juice is there, what is the taste value of this juice, does it smell or not, is the packaging all right, is the printing of the packaging all right. You can judge all of these variables, but you're not going to do this to all of the variables. You're going to do this to some of the variables. That basic process of reducing the number of variables you're going to judge to give you a statistical output is basically what is called sampling. That's the statistical word. uh, I do not know what hypothesis testing is, but I think you are correct. This is very much simple. Like let's say if you're trying to buy mango from a vendor, you pick up 2 or 3 and try to smell them. That's one way to do that. You try to smell them, do they smell good or not? The vendor is going to pick up a lot of mangoes from their jhaga to sell you, but honestly, you don't smell all of them. That's sampling. So what we're going to do, sampling frequency basically means that how often are we going to look at the original signal? How often are we going to take the information out of the original analog signal? For this example, we have used a signal, a sampling frequency. I'm going to write this up over here. For these examples, we have used a sampling frequency equals to 8 kilohertz. 8 kilohertz means we're going to look at the original analog signal 8,000 times every second and pick up the instantaneous voltage value of those instances. 8 kilohertz মানে হচ্ছে তাহলে আমাদের consecutive দুটো অবজারভেশনের মাঝখানে টাইম গ্যাপ কতটুকু হবে? What will be the time difference between 2 consecutive observation? That will be 1 by 8,000. This gives you 125 microsecond. I know these values because I've been teaching this for a very long time. You can calculate this out and check for the correctness of these values. So what is happening over here? We are currently observing the value of this voltage after every 125 microsecond interval. So this is the original analog signal. This is fed into a observation device. Let's say at 0 second we observe 8 volt. At 125 microsecond, we do not observe anything in between. We allow 125 microsecond to pass by. After 125 microsecond, our device analyzes the signal again, and then it gets 12 volt. Then another 125 microsecond, 14, 12, 8. So after every 125 microsecond interval, we get these values of the voltage. So this graph to this graph, this is basically what a sampling is. So we have converted a full continuous graph into vertical lines, instantaneous values. Now we have to convert each of these instantaneous values into binary. So there is a manual way how to convert binaries into the decimal or decimal to binary. I do not want to show you the manual process because it takes time and you don't have to show this ever. You can simply have to know how to use it for the calculator. So if you want to learn how this is done manually, you can look up some YouTube videos. There are a lot of good videos for those. For those who don't know how to do this thing, pick up your calculator. It can be a silver calculator, natural display, or it can be a 911 MS, which I am using. You turn this on, and before you do anything, have a look over in your calculator, the black buttons. On the second row of the black buttons, the button that is actually reads x square, on top, on the upper right corner of the x square, you should see green writing, DEC. This one means decimal. On the right, the second one, which is usually, I think, আমার এখানে লেখা মুছে গেছে, x to the power n মনে হয়, I forgot. আমার লেখা মুছে গেছে. So we have decimal, then we have hexa, then we have bin. Let me just show you what I mean. Wow, it all rhymes up. Okay, this is what I'm talking about. You see this one here, decimal. This is the decimal. This is the hexadecimal. This is the binary. This is the octal or octal. I forgot. This is for 8-base numbers. These are the 4 different things which are going to be helpful for us. So if you're trying to convert one type of number into another number, what we're going to do first, we turn on the calculator, and you should see in the calculator, somewhere in the calculator, if it does not show anything, it means that your calculator currently in computational mode. If you simply press the mode button, you will see a lot of options coming up, and you have to go in the base option of that thing. So I can change this in this calculator, that the one that I have, by pressing the mode button twice and then going for the base. So you have to press the mode button till you get to the base option, and you should now see your calculator should show you the base option, and on the either on the top or on the side you should see the writing that তোমাদের ক্যালকুলেটর এটা কি ডান পাশে দেখায় নাকি উপরে দেখায়? কেউ কিন্তু এই বেস লেখাটা কি উপরে আসে নাকি ডান পাশে আসে? আচ্ছা, বলতেছি, if you আমি এখন তোমাদেরকে কেমনে দেখাই, এটা কি এটা হচ্ছে 99 ইয়েস তাই না? আচ্ছা, মানে ন্যাচারাল নিচে ডান পাশে। আচ্ছা শোনো, for those of you who use a black calculator which is 991 MS, which I'm using right now for the black ones and these ones, here it shows over here, এই যে এখানে টু দি পাওয়ারের জায়গা যেটা থাকে যে এই জায়গাটাতে আসে, আর যারা হচ্ছে এই ন্যাচারাল ডিসপ্লে ক্যালকুলেটর করছে মোস্টলি এদেরটা উপরে লেখা আসে, রাইট? এটাতে কোন জায়গাতে আসে? Did someone could someone go to the base command and tell me why it shows up over here? I don't have this calculator, honestly. I don't use it often. এটা ডান পাশে আসে? আচ্ছা, okay, fine. So it also shows in the right side. So what I want you guys to do is that by pressing the mode button and going to the base N option, you should find out that on the right side of this calculator, you should see let's say this one. I'll pause the resume recording. Sorry. So we converted these numbers into binaries, and they have to be 4-bit. So to make them 4-bit, we have to add extra zeros in front of them if they are not by default 4-bit. So that's why the extra 2 zeros are here. Here we have these zeros are coming in to make them 4-bit. Then we're going to send these binary numbers with some processing into the communication channel. That can be optical fiber channel, can be a wire-based channel, can be a telecommunication channel, microwave channel, any communication channel, and it will be received on the receiving end. On the receiving end, we will recreate the signal by converting these numbers into relevant decimals. So 1000 will be converted to 8, and important part that whenever this series of decimal of binary values will be converted back to the analog signal, we have a value of the voltage at 0 second, which is 8 volt. 1000 converted to decimal gives you 8. We do not have any value for the next 125 microsecond, which means this 8 will remain same for the next 125 microsecond. At 125 microsecond, we have another value, which is what? 12 volt. So it immediately jumps to 12 volt and remains 12 volt for the next 125 microsecond. So whatever the value that you get, it will remain that value for the next pulse. It keeps on happening. So for at 0 second you get 8, it remains 8 for the 125 microsecond. Then you get 12, it becomes 12, remains 12 for the 125 microsecond. And you get 14, then 12. So that's how we're going to assign the values and continue that value for that amount of time duration up till which we don't have another signal value. And this creates this signal, which is somewhat similar to the original signal. There are ways we can make this signal appear more to this signal. This step size, this zigzag rectangular block type kind of shape of graph has a specific word to this. It's called grainy. not granny, grainy. Where is that word? The output of the DAC, digital to analog conversion, is grainy and is not smooth. So it is not smooth as this one, but we can increase the smoothness of this graph or decrease the graininess of this graph by doing some specific things. So we're going to also see those things in the next class. But this is a very basic conversion process for how digital conversion is done. So we have the analog signal, we chop it with the sampling frequency, we convert the sampling voltages to binary, we transmit this binary over combination channel. On the receiving end, we convert that binaries into decimals, which is not shown over here because this would be just the other figure over here. And then those values are used to recreate the original analog signal, which somewhat looks like the original signal. এটি পর্যন্ত বুঝা গেছে কিনা? I hope so. So that's pretty much it for today's class. I'm gonna stop the recording over here